on to page 2. If you didn't write down these equations in class, here they are. Pause this if you need to be at this part longer. So to start with this, remember our strategy. It's always to go through and pick out our variables and say, what variable is this? 20 kilograms. What variable is that? Well, it's a mass. And height of 6.5 meters. What variable is that? Well, it says height of, so it must be an h. I honestly don't have to read the question to at least be able to start with the idea that which equation has m and h? Only the EG equation. But reading the question, it says, how much work would it take to lift a 20 kilogram sack of potatoes vertically to a height of 6.5 meters? So even if I didn't know this was work, you could start with something that you do know, which is that EG equals mgh. And we could plug in our variables. M is 20. Our G is always 10 if we're on Earth. And our H in this case is 6.5. So I get an EG total of 1,300 joules. And then you look back at the question. Did I answer it? Did I say how much work it would take to lift a sack of potatoes up to a height of 6.5 meters? How much work? Well, in fact, I did, because both work and energy gravitational are measured in joules. So I actually did say exactly the amount of work. If we were to calculate this using the work equation, work equals force times distance, the force of gravity of the potatoes is 20 times 10, and the distance would be that I'm lifting it is 6.5. So what's my total here? Well, once again, it's 1,300 joules, because the amount of work I do on something is the amount of energy that it has when I'm done doing that work. And if I am not adding energy to something, I'm not doing work. And if I'm doing work, I must be giving energy to something. So it's really important to recognize that. It's going to be important as we move on to notice that the work we do is the amount of energy it has. All right, for number 2, 1 kilogram pencil is the mass. 40 newtons of force is, of course, a force, because it says of force. And 2.25 meters. Now, meters is going to be our weird one, because meters could be a height, it could be a distance, and it could be a K. It could be a stretch, right? Any of those could be measured in meters. But I'm pushing a pencil with 40 newtons of force for 0.25 meters. In this case, it is a distance. If I said I was lifting it up, then it would be a height. And if I said I was stretching a spring, then it could be a stretch, but it's definitely a distance. You could also just go straight to the work equation. Work equals force times distance. What's my force? Well, I've got it here. It's 40. And my distance is 0.25. So this is 10 joules of work. Work and energy are both in joules. That's not a coincidence. Number 3 is a trick question. We got 20 kilograms mass, 3 meters distance. How much work would be done on it? This is the idea that we only do work if we're giving energy to something. So if I lift the sack of potatoes up, like in number 1, then I've done work. But carrying the sack of potatoes sideways does not actually add energy to it. Sure, they're moving for a little bit, so there's maybe a little bit of kinetic energy, but we're not throwing the potatoes. We're just picking them up and carrying them somewhere else. Carrying actually requires no work. The force and distance have to be in the same direction for us to actually do work. So if I lift it up, that's work. If I carry it over, it's not. All right, on to number 4. And this is one of the questions that the whole question is here, and then I've broken it into 2 pieces so that you can walk through this. But this is the strategy you're going to need to use. I'll just ask the question without the pieces, and you're going to need to figure it out. So I want to get a couch, mass equals 400 kilograms, so obviously that's a mass, onto a truck that's 1.5 meters off the ground. Again, we've got meters. Is that a distance or a height? Well, it's off the ground. Height, by definition, is how far we are off the ground. So this must be a height. I can only lift with a force of 1,500 newtons. So, of course, that must be a force. So I've got more variables than I need right now. How long should my ramp be? So we're often with these conservation of energy questions, we're not going to be able to go straight to how long the ramp should be. We've got to solve with what we have. Mass is 400 kilograms. Height is 1.5 meters. That means we can find an EG. And I want you to do that even if you're not sure what it means yet. Part of being a physicist is working through things. I've got an M and an H so I can calculate EG. So I'm going to do that. What kind of energy do we need to transfer to the couch? Well, we need to lift it off the ground. We need EG energy, and that's mgh. So I'll put in my mass of 400, my g of 10, and my h of 1.5. And when I do that math, I find 6,000 joules of energy that I need to get transferred to the couch. And if you weren't going with this help here, you would go, okay, 6,000 joules of energy. That's how much energy I put on the couch. So I put this fill in the blank here to help you out. That energy that you just calculated is also the what required to lift the couch. The work required to lift the couch. Because if we give energy to something, we're doing work on it. So the formula, I was almost going to write F times D. I saw a lot of students do this. You need to make sure when you write a formula or an equation that we write the whole thing. Work equals force times D. And it's very important we write the whole equation, especially in this case, because we're not going to just multiply the force times the D to find the work. We're actually finding the distance. How long should my ramp be? We're trying to find the distance. So work equals force times D, we need to plug into this equation the work done. I just said it. The energy is also the work required to lift the couch. So 6,000 equals, what's my force? Well, let's look back up at the problem. Force of 1,500 newtons. That's the maximum force I have. 1,500 newtons. And then times D is what we're actually solving for. So we do the algebra, divide both sides by 1,500, and we get a D equal to 4 meters. And because it's a distance, it's got to be measured in meters. So walk yourself through it. Solve what you can, and then you're going to have to do something with that energy. Unless the question asks you how much energy it has, you're probably going to have to take another step and say that energy is another type of energy also. All right, so if I want to throw a 0.5 kilogram disc with a velocity of 30 meters per second, what energy is that? Let's go ahead and label these. We've got mass. We've got velocity, right? It has to be. It says velocity of. I just want to kind of cut this off from the other problem. So what energy is that? Well, it's EK, right? Anything moving, anything that has a velocity must have EK. And EK equals 1/2 mv squared. And the distance of the launching pad is 2 meters, so that must be some kind of distance. But we're not going to use that to figure out the energy that we need. How much energy do I want to transfer? We can't go straight from force to how fast it's going, but we can get there another way. So EK equals 1/2 mv squared. I'm going to go through and plug it in. What's my mass? 0.5 kilograms. What's my V? 30 meters per second, and I'm going to square it. And of course, I need to multiply by 1/2 to get the EK. And this equals 900 times a quarter, which is 225 joules of energy. 1/2. So we got to square first. So important that we square first and then multiply by the other numbers. So 225 joules is how much energy I want to give it. Force required. Which of my equations has force in it? If you get totally lost, you don't understand which equation has force in it. We always want to write our equation down, and it's going to help, I promise. Which equation has force in it? Well, there's force of the spring, but is there any spring involved here? No. So we need to use the work equals force times distance formula. Work equals force times distance. And there's force, that's what we're looking for. And we've got a distance of 2, and then you just have to recognize that the amount of energy we want to give something is how much work we have to do on that thing. So this is this. 225 equals F, which is what we're looking for, times 2. So how much force is required? We divide both sides by 2, and we get a force equal to 112.5 newtons. Force is always measured in newtons. All right, moving forward to the spring practice. Now we're looking at springs, and I won't have these sections on the test, but I wanted to kind of give you some help here. How much force and elastic potential energy will there be in a trampoline K equals 800 newtons per meter that is stretched 2 meters downward? Rewrite the formulas first. And I put that so that you would get in good habits about F spring equals K times X. And E elastic equals 1/2 K times X squared. And when you do this, when you write the equation down, you can really see what we need to plug in. Here's K, and it's stretched 2 meters. X is stretch. So you can solve these pretty quickly. This one's simply 2 times 800, 1600. What's my units? It's a force. Must be newtons. For this one, the 2 is squared, 4 times 800. This one is also 1600, but it's joules. And this is a coincidence. I shouldn't have used a stretch of 2 meters because that makes the energy equal to the force. It will not always be equal. In fact, it very rarely will, because this is a quadratic relationship with stretch, and this is a linear one. But it happens to be the same on this one, and if I'd planned better, I wouldn't have done that. All right, moving on. And I do want to pause for a second and say, you shouldn't be just copying down what I've put. You should work out ahead, try to solve these problems, and then hit play again on this video and review what I've said. Because if you get it wrong, even if you get it wrong, that struggle is so important to bettering how you understand this. All right, so let's move forward. A spring with spring constant K equals 200 meters, so that must be K. It's pulled on with a force of 200 newtons, F. How much will it stretch? That's what we want to know, which is our X. And that's why we use X for that, because we can't use distance, and we can't use S because it looks like a 5. All right, so use your answer describing. This question is a perfect example of why we have to write the whole equation first, and I messed it up the first time. So when we've got K and F, and we're looking at how much it's stretched, this must be the equation we're using. So if we write the whole equation, F equals Kx, then we can start plugging things into both sides, because we're not always going to be just given these two. So F is 200, and that equals our K of 200 times the X, however much it stretches. So when we do that algebra, we get X equals to 1 meter. 1 meter of stretch. And what was our newtons per meter? What does the spring constant mean? It means that if we put a force of 200 newtons, that's how much it takes to stretch the string 1 meter. Spring 1 meter. It's 200 newtons per meter. And look, we did a force of 200 newtons, and we stretched it 1 meter. That's what the spring constant means. So what is the K value of a spring that has 100 joules of EE when compressed a distance of 2 meters? Okay, well, I see EE, so I can immediately write the EE equation. That should be your habit every time, is to write down whatever equation you know. EE equals 1/2 Kx squared. And so I have the EE, 100 joules. 100 equals 1/2 K times 0.2 squared. I've got to square my 0.2 first. 0.2 squared is 0.04 times 1/2 is 0.02. So I get 100 equals 0.02 times K. And then I can solve for K. All I did was multiply all these numbers together to get 0.02. And then we just divide both sides by 0.02. And the K must be 100 divided by 0.02 is 5,000. Really big K. Some springs have very, very big Ks. 5,000 newtons per meter. Use the test to take the test. If you can't decide what units something has like K, go find, oh, K equals newtons per meter. Newtons per meter. You always want to be jumping around like this in physics and trying to solve these like this. It's really, really important.